Welcome to POWTECH Virtual Talks. Dr. Thomas Luxbacher is talking about rare earth ion adsorption on magnetic nanoparticles, a multi-analytic approach. Have fun and enjoy the talk.
Last speaker is Dr. Thomas Luxbacher from the Anton Paar company. Anton Paar is a manufacturer of scientific instruments that cover a variety of measurement techniques from liquid density, rheology, or structure analysis by small angel X-ray scattering. Dr. Luxbacher, who is currently the principal scientist for surface charge and zeta potential at Anton Paar, received his 3D degree in technical chemistry at Graz University of Technology in Austria, and looks back at almost 20 years of experience as a product manager in different areas. He will talk about rare earth ion adsorption on magnetic nanoparticles, and he will give us a multi-analytical approach. Dear Mr. Luxbacher, you may start, please.
Thank you, Mrs. Reutner, for this introduction. Yeah, good afternoon to Shanghai. I'm indeed very pleased to have this opportunity to contribute somehow to IPB 2021, although unfortunately only from remote. The topic of my talk will be semi-scientific and will introduce a promising method for the recovery of heavy metal ions, especially of trivalent rare earth ions, from dilute aqueous solutions. I will introduce a category of nanoparticles with a magnetic core and a functionalized shell as a high surface area adsorbent for metal ions, and I will also demonstrate their characterization by the combination of selected analytical techniques. Before starting with this characterization of materials that contain rare earth elements, I will briefly introduce the company Anton Paar, who offers a variety of different solutions, as Ms. Reuter has already mentioned, for material characterization. And in order to start, I have selected a few appetizer applications, which are the microwave-assisted synthesis of nanocatalysts made of gadolinium-doped cerium oxide, then the analysis of the particle size distribution of a magnetic powder by laser diffraction, and the application of the magnetic mode of an atomic force microscope for mapping the magnetic landscape of a heterogeneous metal oxide at the nanoscale. And finally, I will conclude my talk with a novel approach of magnetic nanoparticles for the recovery of rare earth elements from dilute aqueous solutions, and I will use neodymium as a representative rare earth ion. The company Anton Paar manufactures, sells, and supports scientific instruments. It was founded in 1922, so almost 100 years ago, and meanwhile has grown to an international company with more than 3,400 employees worldwide. Today, the company is owned by the charitable Sandner Foundation. It has an export rate of 95%, and we do continuous investment into research and development. It's important to note that all critical instrument components are manufactured in-house, either in 9 producing companies, which include the headquarters in Graz in Austria. As a user of an Anton Paar instrument, you will get support by either one of 32 Anton Paar subsidiaries worldwide, or one of additional 50 distribution partners. Among the product range of Anton Paar, we find instruments for microwave-assisted digestion, as well as microwave-assisted synthesis. And in this first example, we want to make use of the so-called monowave 400 to prepare catalytically active nanoparticles for the oxidation of hydrogen chloride. Now, the intended end product should be composed of cerium oxide with different concentration of gadolinium as a dopant. And the presence of gadolinium in cerium oxide helps to tune the capacity of this rare earth oxide to store oxygen. Now for the preparation, the proper amounts of cerium nitrate and of gadolinium nitrate were mixed in a microwave vial with some dispersant, which was oleulamine. And afterwards, using microwave assistance, this mixture was heated for 1 minute at 90 degrees Celsius. Then diphenyl ether was added to this mixture, followed by another 1 minute of heating at 200 degrees Celsius. So you see, after 2 minutes, we have received our nanoparticles, which makes this microwave-assisted synthesis very distinctive and characteristic for its rapid preparation of novel materials, and with a significant yield, and with the option to scale up the preparation from some milligrams to even kilograms of product. Now, in our application, the obtained nanoparticles have been harvested by first centrifugation and drying, and were characterized in terms of its hydrodynamic diameter, which was about 20 to 30 nanometers. And in a subsequent process step, this nanocatalyst was embedded in polyethylene oxide nanofibers, which were obtained by electrospinning prior to its use for the oxidation of hydrogen chloride. So if you're interested in this application and you want to know further details, I kindly refer you to this paper, which was published by the group of Professor Smarsley at the University of Gießen in Germany. Once we have prepared our sample of a rare earth element containing material, either by microwave-assisted synthesis or by any conventional preparation route, we need to characterize the material's properties, for instance, the size of a powder sample. And the convenient technique to do so, as you have already heard today, is the optical method of laser diffraction. And the instrument that Anton Paar offers, which is PSA 1190 for liquid and dry particle dispersion, is one option to do so. Now, Ms. Jenny Gang of POWTECH has already introduced the method of laser diffraction in very detail. Just briefly, the laser diffraction method for particle size analysis is based on the principle that the diffraction angle depends very strongly on the particle size. And larger particles provoke a smaller angle of diffraction, while smaller particles show a larger angle of diffraction. And for an assembly of particles, we obtain a diffraction pattern with a specific intensity distribution and use an appropriate model that we apply to convert this diffraction pattern into a final particle size distribution. Here you see the size distribution of a powder sample of a samarium cobalt alloy, which was determined for dry powder using the Venturi principle for generating a particle aerosol. Already today, it was mentioned that the preparation of a powder dispersion is key for a successful measurement of the particle size distribution. In this example, we have explored the effect of a different air pressure on the final size distribution. By using a pressure of 1.5 bar, we observe this heterogeneous but highly reproducible size distribution. Upon increasing the air pressure to 2 bar, we realize a further resolution of the peak that is located at 300 micrometer into 2 peaks with maxima at 200 and 400 micrometers. The other size fractions of this heterogeneous powder shows peaks at 18, 40, and 100 micrometers. When we now look at the cumulative particle size distribution, curves for powder aerosols generated by either 1,500 or 2,000 millibar of pressure, and when we extract the characteristic descriptors of these size distributions, we find only marginal differences in the D10, D50, and D90 threshold values. And we conclude that the higher pressure which we applied for getting a better dispersion of the powder sample, did at least not destroy any of the individual particles. In the next processing step, the synthesized and characterized particles are then transformed into the final material component, such as a thermoelectric, like a gadolinium-containing calcium manganese oxide. By using the instrument Tosca 400, which is an atomic force microscope, we attempted to map differences in the magnetic response across the surface of this oxidic compound. For this purpose, we put sample fragments of calcium gadolinium manganese oxide into a polymer resin and polished this fragment of samples. The copper strip that you see in this picture was only used to perform some additional conductive mode measurements using the atomic force microscope. So it's not important for the magnetic mode of measurement. But this is the mode of this atomic force microscope that we have used to characterize the material surface where we expect different magnetic domains. For this purpose, we use an oscillating cantilever with the atomic force microscope tip covered by a hard magnetic coating. In the first pass, the cantilever is operated in the classical tapping mode and detects the surface topography. Afterwards, the cantilever is lifted, and in the second pass, the cantilever again oscillates, but now parallel to the surface at a constant distance. And the magnetic interaction between the cantilever tip and the magnetic domains of the material determine the final phase signal. The mapping of the topography, which you see on the left-hand side, using the conventional tapping mode of the atomic force microscope, shows some grooves and scratches, probably from the grinding and polishing process of the sample preparation, as well as some elevated and lowered positions that represent particles, pores, and holes in the material surface. The same area of 2.5 by 2.5 square micrometers was scanned by the cantilever tip with the hard magnetic cobalt coating. And the phase plot obtained from the magnetic force microscopy shows areas of different magnetic response, which coincide with the topographic structure of this material surface. In the remaining part of my talk, I will now illustrate the approach of collecting rare earth ions at low concentration in aqueous solutions by the adsorption on magnetic nanoparticles. Among other techniques for characterizing magnetic nanoparticles and the adsorption of neodymium ions, we have used the instrument Light Sizer 500 for the characterization of the size and the charge of these nanoparticles. The idea of using such magnetic nanoparticles for the collection of heavy metal ions from aqueous solution, such as industrial wastewater, is motivated or triggered by the ease of separation of these particles with an external magnet. The nanoparticles furthermore offer a very high surface area, and we may apply or have applied a so-called core edge shell concept to functionalize the magnetic core by an appropriate surface chemistry, thereby enhancing the selectivity of the magnetic nanoparticles towards specific metal ions. As I have already mentioned, the driving motivation of using magnetic nanoparticles is the straightforward separation of these particles by an externally applied magnetic field, and furthermore, the possibility to easily regenerate these particles for multiple uses. The results that I will show were experimentally approached by a recent master thesis that we have done in collaboration with the University of Maribor in Slovenia, a neighboring country of Austria, where we have focused on the recovery of neodymium as one of the economically most critical rare earth elements, as we have already heard before. We are certainly happy about the characteristic peaks in the UV-vis absorption spectrum of neodymium that help us very much to determine the efficiency and the kinetics of its adsorption on magnetic nanoparticles. The starting material for the preparation of the magmite magnetic nanoparticles is a mixture of iron 2 and iron 3 chloride. By a co-precipitation method of these iron salts, followed by a stabilization of the nanoparticles in ammonia solution, we now first generate the magnetic core. In a subsequent process step, the nanoparticles core gets now covered by a silica shell that carries amine functional groups for the complexation of heavy metal ions. The nanoparticles were characterized by different methods such as thermogravimetric analysis and attenuated reflection Fourier transform infrared spectroscopy, which clearly indicates the difference between the naked magmite core particle and the final core edge shell magnetic nanoparticle. We have also recorded the ATR, FTR spectrum of magnetic nanoparticles after adsorption of neodymium and observed an additional characteristic peak at 1307 wave numbers. To determine the size of the primary particles, we use transmission electron microscopy that indicates an average diameter of these primary particles of 9 nanometers. But when we disperse the nanoparticles in an aqueous solution, a certain degree of aggregation takes place immediately, and the hydrodynamic diameter of these aggregates, which is determined by dynamic light scattering, is observed in the range of 250 nanometers. We have now proceeded with the analysis of the pH dependence of the particle size in order to cover different aqueous conditions for the neodymium ion adsorption process, which depends on the feed solution, on the wastewater solution, for instance. When we move to higher pH, for instance, we observe a sudden increase in the hydrodynamic diameter, which shows some kind of peak at 3 micrometers, which occurs around pH 9. By decreasing the pH, we observe some reversibility of the particle size, but also a kind of hysteresis, which delays the approach of a particle size of 250 nanometers to a lower pH of 6. How can we understand this hysteresis or also the change in particle size with different pH? In order to elucidate this pH dependence of the particle size, we have determined the zeta potential in parallel by measuring the electrophoretic mobility of these particles. The zeta potential correlates with the charge at the particle-water interface and is responsible for the electrostatic interaction among alike particles or different particles and solutes that are present in the aqueous solution. The initial zeta potential of the magnetic nanoparticles reads plus 28 millivolts, and this is representative for the protonated amine groups of the functionalized particle surface. By increasing the pH, we find a decrease in the zeta potential, which approaches 0 millivolts at the so-called isoelectric point, which occurs at pH 9.8. With the diminishingly small zeta potential, the electrostatic repulsion between nanoparticles becomes weaker and particle agglomeration takes place. And this is evident by the increase in the hydrodynamic diameter with increasing pH. As for the particle size, the evolution of the zeta potential with pH is also almost reversible and shows similar hysteresis that we observe for the hydrodynamic diameter. We finally conclude that the exposure of these magnetic nanoparticles to alkaline conditions somehow affect the amine functional groups to a certain extent. The measurement principle of dynamic light scattering for particle size analysis relies on the Brownian motion, which is a random motion of particles dispersed in a liquid. And the primary parameter that is determined by dynamic light scattering is the diffusion coefficient of these particles, which is related to the hydrodynamic radius or the hydrodynamic diameter of these particles by this Stokes-Einstein equation. Opposite in electrophoretic mobility or electrophoretic light scattering, we apply an electric field on the nanoparticle dispersion. And the particles move according to their net charge, either towards the positive electrode if they are predominantly negatively charged, or to the negative electrode in case of positively charged particles. In electrophoretic light scattering, the electric field is reversed, but at a much higher frequency, as you can see here for this video, which was recorded for a microelectrophoresis experiment using an optical microscope. For the calculation of the zeta potential, the particle velocity is related to the electric field, and this ratio is called electrophoretic mobility, which is related to the zeta potential. We just need to know the viscosity and the dielectric property of the aqueous solution. Finally, we have performed some adsorption experiments by adding magnetic nanoparticles to an aqueous solution of neodymium nitrate, and we used UV-vis absorption spectroscopy to detect the depletion of neodymium in solution. And we have used the peaks at 575 and at 740 nanometers to first establish a calibration curve that correlates absorbance to concentration of neodymium in solution. In the adsorption experiment, we have exposed a solution of 0.05 mole per liter of neodymium to a sufficiently high amount of magnetic nanoparticles for a specific time. And after removing the nanoparticles with an external magnet, we obtain a remaining concentration of 0.035 mole per liter, which corresponds to a removal of neodymium ions by about 30%. In summary, this core at shell concept of functionalized magnetic nanoparticles is promising for the capture of heavy metal and rare earth ions from dilute aqueous solutions. However, we observed that the intended removal of magnetic nanoparticles by an external magnet is not quantitative due to the fraction of small-sized particles which require the additional application of a centrifuge or even a filtration with a 20 nanometer filter, because remaining nanoparticles in solution with adsorbed rare earth ions may change or falsify the conclusion on the removal efficiency for these ions, since they contribute to the absorbance of neodymium in UV spectroscopy. To determine the neodymium ion concentration in solution, it is rather simple and reliable using simple UV-vis spectroscopy. For other rare earth ions, however, that do not show characteristic peaks in the UV-vis spectrum, we may need some kind of other techniques, some other optical techniques like excitation spectroscopy in order to provoke some luminescence, or we have to use some kind of colored complexes in order to visualize the presence of these rare earth elements. I'd like to conclude my presentation with a small review of the instruments and solutions that Anton Paar offers for powder and particle characterization. So you have learned about microwave-assisted synthesis for nanoparticle preparation, which was possible to do with the monowave 400. For particle size analysis in a range of 40 nanometers to 2.5 millimeters, we use the PSA series for laser diffraction. Then I have introduced the atomic force microscope TOSCA 400, which is a versatile tool for studying different material properties, but also, for instance, particles that get adsorbed on solid surfaces. With the light size of 500, we again measure particle size, but in the sub-micrometer range, as well as the zeta potential and charge of particle dispersions. Other instruments that enable or complement powder rheology, or the analysis of surface area and pore size, or the structure, the crystalline structure of your material by X-ray powder diffraction, or even a smaller structure by small angle X-ray scattering are also available. So thank you very much for your kind attention.
Thank you.